Welcome to The Explainer. Today, we're diving into a really fascinating biological mystery. Why exactly does our skin's collagen break down so incredibly fast as we age? We usually think of skin aging as this super slow, inevitable wearing out of parts over decades. Just standard wear and tear, right? But the science is showing us something way more dynamic and honestly way more catastrophic happening right beneath the surface. It's a rapid, accelerating decline. So today, we are going to uncover exactly why skin collagen declines so fast, and we're doing it by looking straight at the cellular evidence.
So let's just get right to it and ask the core question. What triggers this sudden compounding loss of elasticity in our skin? It isn't just a matter of producing less collagen over time. The wild part is that our existing collagen is actively being destroyed at an accelerating rate, while new production gets completely shut down at the same time. To understand why this happens so fast, we really have to look at the mechanical environment our cells are actually living in.
Which brings us to part 1, the skin's support network, specifically the extracellular matrix.
To solve the mystery of this sudden collapse, we first need to check out the scene of the crime, the extracellular matrix, or ECM. Think of it like a massive 3D physical scaffolding made mostly of these thick collagen and elastin fibers. Now, the resident cells in there, called dermal fibroblasts, are basically the construction workers of the skin. But they aren't just floating around aimlessly. They act more like climbers clinging to a suspension bridge. They use these specialized transmembrane proteins, specifically integrins, to physically grab onto the collagen fibrils. By anchoring to the ECM, they pull against it, which generates internal mechanical tension. And this mechanical tension is absolutely crucial. It's the literal physical signal that tells the fibroblast, hey, stay active and keep pumping out new collagen.
And the contrast here is just stark. Youthful skin relies completely on this highly organized, high-tension environment. The collagen fibers are intact, giving the fibroblasts solid anchors so they're stretched out and actively building new matrix. But look at the aged skin environment. Over time, UV radiation and native enzymes come in and start fragmenting those long collagen fibers. Suddenly, the scaffolding is broken, the fibroblasts lose those vital anchoring points, and the whole physical support system is destroyed. The tension is just gone.
And that structural deterioration leads us right into part 2, the great cellular collapse, the actual loss of physical tension.
It's amazing because we can actually see this exact process happening under a microscope. Check out the healthy fibroblast on the left, sitting on a stiff, intact matrix measured at 15.3 kilopascals. Notice how stretched out it is? Its edges are actively reaching out, gripping the surface, generating immense traction force. But then, compare that to the deflated cell on the right. This is a fibroblast on a soft, compliant, fragmented matrix, exactly what we see in aged skin. It's lost its anchors, it is totally shrunken and completely rounded out.
So when those collagen fibers break, these cells literally lose their grip. Because they can't pull against a stiff matrix anymore, all that mechanical tension vanishes. And this physical collapse into a shrunken, rounded shape, it's not just a superficial change in how they look, it is a massive shift in how the cell behaves. That physical collapse causes the cell to completely shut down its standard healthy operations.
Which triggers a nightmare scenario. Part 3, the vicious degenerative cycle. A feed-forward cascade.
The really crucial point here is that this cellular collapse isn't some isolated one-off event. It kicks off a disastrous feed-forward chain reaction. Let's walk through how this vicious cycle actually builds. Step 1, you get initial UV or age-related damage causing minor collagen fragmentation. Step 2, the fibroblasts lose their physical tension. Step 3, the cells physically collapse. But here is the critical fourth step. That sudden loss of physical tension acts like an emergency alarm, directly upregulating a transcription factor complex called AP1. AP1 hits the panic button and pumps out massive amounts of collagen-degrading enzymes. These enzymes then go out and destroy even more of the surrounding matrix, which breaks more anchors, forcing the neighboring healthy fibroblasts to lose their tension and collapse too. Step 5, the whole cycle repeats, just faster and faster.
Like I said, the collapsed cells essentially panic. Laser capture microdissection of aged human skin shows this massive wave of matrix metalloproteases, or MMPs, being unleashed right into the dermal layer. We're talking massive, sweeping elevations. MMP10 is up, MMP3, MMP1, they are surging. And to make matters worse, this surge isn't accompanied by the natural inhibitors called TIMPs that usually keep these enzymes under control. The result? Completely uninhibited collagenase activity. These collapsed cells are actively dissolving the very scaffolding that's supposed to keep the skin tight and youthful.
But wait, Enzymes chewing up the existing scaffolding is only half the story. Part 4. The chemical culprit. Prostaglandin E2, or PGE2.
Because as these fibroblasts lose their mechanical tension and physically collapse, their internal metabolic profile shifts drastically. This sudden mechanical relaxation causes the cells to dramatically ramp up their expression of cyclooxygenase 2, or COX-2. And that leads to a shocking 70% increase in a lipid signaling molecule called prostaglandin E2, PGE2, in elderly skin compared to young skin.
And the data definitively backs up this chemical shift. We can actually track the mRNA expression of PTGES1, which is the specific enzyme responsible for synthesizing all this PGE2. There's a highly significant progressive spike as chronological age increases. Through cell sorting, researchers actually proved that the dermal fibroblasts themselves, the exact cells that are supposed to be building your skin, are the primary source of this massive chemical flood.
And right here is the fatal blow to our skin's elasticity. This explains why the decline is so wildly rapid. This huge surge in localized PG2 actively paralyzes the cell's ability to synthesize new type 1 procollagen. So think about it. Not only are the collapsed cells releasing enzymes that chew up the old collagen, but the resulting PG2 chemical bath completely stops the production of any new collagen to replace it. It's a total structural failure on both ends.
Now that we know the mechanics of the crime, how do we fix it? Part 5, restoring mechanical balance and breaking the cycle.
So how do we actually stop this destructive mechanobiological loop? Researchers are looking at some fascinating interventions. One approach is purely chemical, using topical NSAIDs like diclofenac to inhibit the COX2 enzyme. This effectively blocks that PGE2 synthesis, taking the brakes off and allowing the cells to restart collagen production. But we can also intervene mechanically. Injectable cross-linked hyaluronic acid fillers are super interesting here because they don't just take up space, they provide direct physical and structural support to the degraded matrix, giving those floating fibroblasts something to anchor to again. And finally, mechanized cyclic strain, literally applying physical mechanical force to the tissue, has been shown to transition those deflated, rounded fibroblasts right back into a stretched, active, collagen-producing state.
The scientific literature makes it crystal clear. These structural treatments show incredible promise. If we can restore the physical scaffolding, whether we do it through fillers or mechanical stimulation, we can stretch those collapsed cells back out. And when they spread out and regain that vital mechanical tension, they wake back up. The destructive AP1 signaling drops, the PGE2 levels fall off a cliff, and the cells get right back to producing fresh type 1 collagen.
So what's the big takeaway here? We've seen today that skin aging is definitely not just a slow, passive fading away. It is a rapid, aggressive chain reaction of mechanical collapse, enzymatic destruction, and chemical paralysis. But understanding this completely changes how we approach skin health. If aging is truly a mechanical collapse rather than simple wear and tear, are we finally entering an era where we can rebuild our cellular scaffolding from the inside out? It's a pretty thrilling prospect. Thank you so much for joining me for this explainer, and keep exploring the incredible biology happening right beneath your skin.
Follow and subscribe for more.